Hello, my name is Mohamed-Achref Maiza, and I am senior data scientist for a world-leading company based in France, and it's actually an automaker. Digital transformation through AI and machine learning should focus first on generating savings through process optimization. This will be very important to invest later in or now in new vehicle features. But you have to make this saving first to invest in new features or mobility services, for example. Automakers can use, for example, car data, analyze it correctly using machine learning to understand what features of a car are being used and what features are not being used correctly. So this will help them understand better what kind of new services they can create on the car, what kind of unique selling points they should focus on to increase their competitiveness and to provide a better product market fit. In addition to that, automakers can then focus on the emerging mobility market because there's a big potential to increase revenues through technology. And for example, using AI and machine learning, automakers can perform more efficient fleet management if we are talking about shared vehicles. And using ML, I will give maybe one or two examples. You can optimize the way you pick up the pickup and the dropout locations of these shared vehicles, and also provide a better price using dynamic pricing to adapt to each rider part. This is a very exciting problem I have been working on recently for manufacturing. Traditional machine vision systems are robust and fast when it comes to analyzing structured scenes. But in general, anomaly detection, when you are dealing with anomaly detection in plants, defects, you can't predict in advance what a defect will look like. So here we have also the human being in the plants, the operators, and the operators have a great capacity of appreciating all the variations in the data, but not really all the variations, and they are still quite slow. So deep learning technology mimics human intelligence. It provides appreciation of all variation in the data and brings automation. So it's like a good combination of human-like flexibility and speed, robustness of computerized systems. But now the question is, how can we train these models, these machine learning models, on small data sets? Because defects are rare, right? So here, with the advance in research in machine learning, there are new techniques emerging called few-shot learning. And using few-shot learning models, you can be able to just learn easier from small data sets. So this kind of techniques I'm working on related to computer vision, and that prove it today to increase the efficiency of machine learning on small data sets. And they will have a great potential to solve many problems for manufacturing. I think safety should be a concept, a transversal concept. Automakers should focus on, but all over the company, in all services. In testing and validation activity, testing plans should need to be optimized in terms of time and volume. We need to be able to run a larger and larger number of scenarios and generate more robust validation results. But also, coming back to manufacturing, in plants, you can enhance visual quality control, visual inspection with deep learning, for example, be able to check 100% of your production. And all this is powered by AI and machine learning where we focus mainly on optimizing outcomes, bringing automation, and discovering hidden patterns in data. So the question is about how can we shrink machine learning models, make them smaller, and increase the speed of the inference of prediction. So there are hardware and software solutions. On the hardware side, there are new devices coming out that can accelerate inference. And I will give maybe two examples. There is the Google Coral Edge TPU, which is an accelerator based on a tensor processing unit. And the tensor processing unit is designed by Google to accelerate matrix multiplications, something that we find a lot on deep learning algorithms. It's all about that. There's also a version called the dev board that looks like a Raspberry Pi, developed by Google very recently. And there's also a product from Intel called Intel Movidius Neural Compute Stick. And this holds a vision processing unit. It's like a new generation of microprocessors designed for vision applications. And this has also the capacity to accelerate prediction inference. On the software side, just before to move to the software side, what is good with these devices, new devices, is that they run also a specific software called TensorFlow Lite. And TensorFlow Lite makes it possible to use existing TensorFlow models. It's a framework to create deep learning applications. So you don't have to just start from the beginning. If you have already a TensorFlow model, you can convert it to a more compressed model and deploy it on mobile devices and embedded systems. There's also another technique, pure software, pure development of machine learning models that the data scientists can use. It's called, it's related to how you build the architecture of your deep learning model, of your neural net. Techniques like one-by-one convolutions can shrink the number of channels in the neural network, make the volume much smaller without losing a lot of efficiency. So it proved to be successful in many deep learning algorithms like Inception, also called GoogleNet by Google. And it made it possible to reduce the computation time by a factor of 10. Yeah, so like you said, there's a bunch of evaluation metrics that can be used to measure the robustness of machine learning algorithms. The way I deal with these evaluation metrics is always to try to create a connection with business impact. Each machine learning problem is different and you have to adapt to it. If you can create or show business impact, it will be interesting for everyone. And if you have, for example, a metric that is based on the false alert rate of your model, you can try to do the exercise to measure the cost of a false alert and try to convert it to another metric that reflects maybe a financial gain or a financial loss. And like that, I think it's very powerful when communicating with business teams and when trying to convince them to use machine learning models. So I think every problem is different, and when it comes to the evaluation of machine learning models, we should always think the real value of AI. We should optimize for this real value at the end. Probably I will think about the design, the styling of the car, the body style of the car. Machine learning models, deep learning especially, has been successful recently in generating art images using what we call neural style transfer. So it's impressive, but I doubt if it will work correctly on designing, generating new styles for the car that will trigger the emotions of the customer and that will comply with the safety, with the aerodynamics, and with the visual signature of the brand. So I think it will be a hard challenge to solve this kind of problems for designers. We still need them.